All right. So let's quickly recap what we talked about the GPU last lecture and wrap up this chapter before we start introducing CUDA. Okay. So we mentioned, right, GPU always have that computing power, but the question is whether and how we can offload our general program to GPU to explore those parallel computing power. And so that's why today we have a library like CUDA, right, provide that programming API and the necessary library to help us run general purpose computation tasks on GPU. And uh, however, because of the GPU server we have today, the CPU and GPU, they basically work independently, they have their own memory and their own scheduler. So you have to pass the data between the GPU and the CPU if you want to utilize the computing power of GPU. So the memory bandwidth and the memory size of GPU become the main bottleneck. And we will talk about that and introduce a couple of optimization techniques in the last lecture of CUDA programming. Okay. And this is a quick view of the GPU architecture, right? We talked about last time that you can see even the GPU architecture is a hierarchical structure, right? Because you have so many cores, and so he used this hierarchical structure to manage those cores. So within the GPU, we have many string processor, and within each SM processor, we have several SIMD processor, which provide the computing core of the GPU. Okay, and in order to make sure the memory access speed can catch up with the computing speed, so besides we have this global memory, we have a per block shared memory within or on this string processor, and also we have register, right, that can only be accessed by threads or by individual core. Okay? So we will see that this is a complicated hardware architecture. So the programming language like CUDA also try to abstract those hardware architecture into some of the programming objects or programming API you will be using. Okay, and this is a closer view of what inside a string processor, and we will definitely see this picture again in the next lecture when we talk about what's a SIMD processor and when do you need to do synchronization. Okay. All right, so that's what we have last time, and we will quickly wrap up this chapter by just giving you a bit more background knowledge about the GPU, especially some of the products and the library from NVIDIA, because that's the GPU and the programming library we're going to use. Okay? And as you can see here, we all know that NVIDIA has pretty much dominated the GPU market right now, and they have many different models of GPU. So which one should you use, right? Especially if you go to a shop, you see so many GPUs, then how can you distinguish and how those GPUs are different from each other? So as you can see over here, mostly the GPU from NVIDIA can be categorized into four categories. Okay, the GPU that's for traditional visualization or image rendering, especially on personal computer. Okay, and this set of products is named after GeForce. So I think most of you are pretty familiar with this type of GPU, right? Because if you want to play some video game on your computer or on your laptop, most likely you are installing this GeForce GPU. Okay, and however, that's just usually just for personal computer or some um, general gaming purpose. But if you want to do some professional rendering, like for movie making or 3D visualization, and then you will use the Quadro GPU. So those GPU are more powerful. Okay, so that's why they are designed for professional image rendering tasks. Okay. However, for the GPU we are using in this course, actually we're using GeForce, but uh, that's because our computing demand is not that large, and we are not really a high performance computing system uh, or the cluster. Uh, we so the However, if you want to have very powerful computing power for general purpose computing, then the model you should choose is called Tesla. Okay, so the Tesla GPUs are designed for general purpose computing, or is what we call the GP GPU, right? And especially those GPU, they are supposedly installed on some powerful server, and the performers are usually measured by the double precision uh, operations. So they are for traditional high performance computing. Okay. However, the general purpose application exists everywhere right now. So some of the computing, right, we want to offload to some embedded device or maybe in the cell phone or on some sensors. Then there are other, the like the Tegra or Jetson, or there are a couple of more. There are more diverse products over here. Those are the GPU for embedded device. Okay. So you can see depends on what kind of application, what kind of computation you want to perform, then you should choose or buy the proper GPU instead. Okay. And the reason is those GPUs are usually customized, optimized for different purposes. Okay. And as you can see, for deep learning, for example, if you want to train a model, then you probably want to choose the HPC, the GPU for HPC computing, right? And that's exactly usually what we installed in the supercomputers or in the cloud platform. Okay. However, if you want to you want to have the GPU power, the processing power on your embedded system for the inference of deep learning, then you should choose another set of products. Okay. All right. So you can see that each type of GPU has their own strengths. Okay. All right. So after you have some idea about what those names coming from. By the way, I forgot to mention this is also important. So no matter which category of GPU you are using, the next thing you should look for is the architecture, right? It's just like which generation of architecture. Okay. So you always name after some scientist. Okay. And actually, the latest architecture is called MPRE. Okay, and Volta, right, is the last generation. So if you see, for example, if a product's named after Tesla V100, then that means it's a GPU for HPC computing, and the V stands for Volta, so it's a Volta architecture GPU. Okay. So by the name, you can tell what generation it is and what's the purpose of the GPU. Okay, so just give you an idea what's the meaning of their name. Okay. And then we will let's look at the hardware specification of those GPU, right? So obviously they are all kind of different, right, in terms of the hardware specification and their performance or their resources. Okay, and you can see, of course, if it's a more powerful GPU like Tesla V100, then you can expect you have more cores, right? However, the core clock is also increased, but not that much. Okay, and also what's important is like the memory bandwidth and the memory size, because as we said, those are usually the performance bottleneck. So people prefer to have a GPU with more memory size and higher bandwidth. Okay? And you can see that actually the bandwidth increased quite a bit recently. This data kind of out of date, but for example, A100, this number is already double or even triple. Okay, but for the memory size as well, it was used to be 16 gigabyte, but for A100, you can go up to 32 or even maybe 64. Okay. And another thing is the bandwidth. You can see this memory bandwidth is the bandwidth between the GPU card. And more importantly is the memory bandwidth within the card, from the stream processor or even from your GPU core to the global memory, okay, the device memory. So you can see that numbers also can be increased quite a bit by some latest technology like the NVLink. We will talk about this more later on, but this is a technology from NVIDIA to replace the PCIe bus, because PCIe bus is designed for general I/O device, and even thought we have Gen 5 or 6 today, but the speed is still increase not that much. Okay, but for NVLink, you can see it can suddenly increase the bandwidth by almost 10 times. Okay, so that's why uh, if you really want to expose all the performance, then you probably need the interconnects is very critical. Okay, another thing is just like the link pack benchmark we talk about for supercomputer. Usually we try to measure the performance by flops, right? And you can measure flops with in the single precision or double precision data type. And you can see this is the difference. For regular image card, actually for if it's for single precision, its performance can be close to those GPU for HPC. However, for double precision, you have a significant gap between the two. So that's why if you for traditional HPC computing, usually you demand double precision. So you would like to use the the GPU card for HPC. But on the other hand, if your computations for just like deep learning, which actually only require low precision data, like single or even half precision, then even using the regular card, can be you can have a performance close to sometimes the same as the card for HPC. So that's probably why you heard about some people actually use this type of card to do deep learning instead of buying the card for HPC. Okay. All right. So of course, and another thing you should notice is the compute capability. Okay. So if you are later generation card, then usually you have a higher compute capability. Okay. So what is a compute capability? We'll talk about this later. Basically, it's um, define, right, the capability of your not just the GPU hardware, but also for the CUDA library, the software. Okay, so it's actually you can say it's a specific specification between the hardware and the software, so they can run together, right? Okay, so you can see here, as we have using those newer version of architecture, of course you have some benefit, right? Not only from the performance point of view, but also sometimes you have better capability. You can do more. You have more more dynamic or more powerful functionalities. Okay, and some of the big differences between those architecture, as you can see, is first of all, right, how they are manufactured. So of course, if you have the fine grain manufacturing technique, then you can build a more powerful GPU, right, by adding more cores or having more memory, etc. Okay, and another thing is, as we mentioned, the interconnects, right? So, like for example, from Pascal, we can start supporting NVLink 2.0, which has over 160 byte per second bandwidth. And if you goes to Volta, then you can use the even faster version of NVLink 2.0 and reach almost 300 gigabyte per second. Okay? And also the technique for those DRAM, your memory, right? So that's why you can have faster and larger GPU memory. Okay, especially for Volta, starting from the Volta architecture, you can even have tensor cores with the GPU. So it's like the accelerator for GPU. So it's even faster, and we will talk about this also later on. Okay. So basically, it's specific design for deep learning because we have so many deep learning are basically always perform those convolution operation. So we might just as well just design a ASIC chip, right, for that purpose. And so that's why it's what we call the tensor core. Okay. All right, and finally, it's the compute capability we mentioned, right? You can see it's basically a specification, about some of the functionality and some of the configuration, right? Such as what's the maximum dimension of a block, right? Or what's the maybe the maximum number of threads within the block, okay? So all those are defined by the compute capability. And of course, as you are, if you are late, newer version, then with a higher capability, then you probably have a more powerful or larger setting for those all these or for all those items. Okay, and some of the functionality, right? So you can see some of the later capability will support those functions, but the older capabilities, uh, they may not support those functions. Okay. So for any GPU, okay, the GPU hardware, if you can look for his compute capability. Okay, it will indicate um, he can support up to what compute capability. And sensing for the CUDA driver, okay, the CUDA library we installed, the CUDA version we use in our computer, installed on our computer, it will shows what's the compute capability supported by this version. So there should be a intersection, right, between your GPU hardware and the CUDA software. Okay, right. And so there's another way to look at those specifications is to use the device query. Okay, in your lab you will actually use it or play with it. Okay, so it's basically just a simple command, and it will shows most of also those information, right? Important information for you. It's probably sufficient for your homework already. Okay, so you can quickly look at here, like the CUDA driver is 5.0, and the capability we talk about, right, is only 2.0 because this is M2090. It's a very old car, so that's why at that time the capability is only 2.0. Today it's already maybe I forgot around 10. So we have advanced a lot over the past few years. Okay, and you can see some of the hardware configuration, right? Like what's the size of your cache, your constant memory, shared memory, etc. So when you do some optimization, you will definitely want to, right, utilize all the cache space or the memory space or the register on that hardware. So you can check how much, right, how much space, how much resources you have on this card. Okay. All right. So so finally, the before we talk about the API for CUDA, so you need to know the CUDA is actually a toolkit. So it includes a lot of things, basically all the things you needed for doing CUDA programming, including the library, the compiler, the sample code, or the debugger, etc. Okay, so so if you need it, basically you should just try to Google it, right, and look up online and see whether there are helpful resources or information provided by CUDA. Okay, and here is just a quick view, in terms of the architecture that that can support it for the compute capability and the CUDA version. You don't need to worry this too much in this class because our TA already set up the environment for you. But you are feel free to use the command we mentioned or some other command you can find from the internet to query the information and maybe to check out the environment of your for your homework, okay, and for your labs. Okay. All right. So that's it for this chapter. So so hopefully, all of you have basic idea about heterogeneous computing and the GPU before we start talking about CUDA.